Okay, so today we will cover chapter 4 and then some part of chapter 5, 1 and 2. So here we'll first of all concerned about the affine uh, space and then some with the ideal boundary of AN, there's some properly convex domain, and then there's some convex domain in AN with the boundary here. And so basically, we will try to use some anosov flow technique to obtain these kind of asymptotic niceness here. Okay, so we'll first of all consider affine action. So we have some affine group acting on affine space. So we consider this as a inside Sn with the boundary being some hypersphere. And the AN is an open hemisphere. So let the U be some properly convex gamma invariant domain. And the its closure intersect with BDN is some convex set like this. See it. Omega is a properly convex open domain. And uh, so and then we assume that this gamma action is of course closed projective orbifold, and the action is said to be properly convex affine. So if there is a U which is invariant under this, then this is said to be properly convex affine action. So this is gamma U omega is said to be properly convex affine triple. So sharply supporting hyperspace P at X is asymptotic to U if there are no other sharpness. So as a subspace of Sn, P prime, so that P prime A separates U and PA. So it's there's nothing that so it is asymptotic ones. So in this case, the hyperspace P is said to be asymptotic to U. And we say A as a space hyperspace to indicate these spaces. Okay, and so let's gamma U omega be properly convex affine triple. And this action is asymptotically nice if gamma acts on this space J, which has to be convex. So this is a affine AS hyperspace is at X, CL omega, and H is not in the Sn infinity. So of course I mean that at every X there is some hyperspace H here. I should make that clear, and then the and also any sharply supporting hyperspace of sigma in Sn minus one. So this is a projective n minus one sphere. So if you have any such thing, then it has to be contained in any at least one element of J. Okay, sure. So that's some set J, and then this set J has to be compact. Okay, so if there's some J where gamma axon, then this is called action is called asymptotically nice, and as a consequence, any sharply supporting M minus hemisphere is uh, is compact and bounded away from PDAN in the Hausdorff metric. So okay, so in the Hausdorff metric, these hyperspaces will be bounded away from these things. Okay, so there's some lower bound on the angle of the sphere. Of course, the angles are not invariant on the projective action, but there still is some angle. Okay, so then the basic theorem we want to prove is so if gamma is a word hyperbolic group, I mean the word hyperbolic group here, properly convex affine action. Well, I should maybe change it later, and then the affine action on the affine sphere, acting on a properly convex domain. Then this is a closed n minus one orbifold, and suppose it satisfies uniform with eigenvalue condition, then action properly convex domain U with the following property. So if you satisfy this condition, then there is this properly convex open domain U, and then this becomes a properly convex uh, triple, and then gamma is asymptotically nice with respect to this. And if you have any other such triple, then the AS hyperspace at each point exists and is same as U. And that is gamma is also asymptotically nice with respect to U prime. So this is word hyperbolic. So actually omega gamma is C1. Uh, so you need to, so each point there is only one sharply supporting hyperspace. And then, so this theorem says that there's only one n minus one dimensional hyperplane containing that plane. Okay, so I will explain the uniform middle eigenvalue condition next. Uh, so let's say subspace is expanding on the linear map if LU is bigger than C for every U in Rn for some fixed norm, and then C bigger than 1. And the contracting map is if uh, is contracting on the linear map if LU is less than C for every U in C for a fixed norm, and then boundary C between this. Okay, so of course this means that there you do this with respect to some norm. So expanding means that there is some norm with this property, and contracting means that there is such a norm. Of course, not non-degenerate norm. And of course, this is same as saying that the norms of eigenvalues are strictly larger than one or strictly less than one in the contracting case. So this is actually some corollary in Katok and Hasselblad, but this is not a big theorem, but it's of course something you need to know. Okay, so uh, this in this section we will work with SN, but the RPM version is very similar to here. So let me explain the uniform middle eigenvalue condition. So affine action means that every you can think of it as a matrix like this affine transformation. So you write it like this. So H hat is some matrix with determinant plus minus one. So I have to divide to make this into SL n plus one minus one n plus one matrix. And then BG is some n times one vector. Okay. And zero is some zero row vector. And then of course in the affine coordinate this will have this form, because if you want to normalize in the affine coordinate, then this is the form you get. And so let's say the lambda 1 is the maximal norm of G. So as a whole matrix here, uh, maybe I should say the H of G, probably better. But um, so I mean, I guess G is already a affine group, so I don't need to say that. But anyway, so okay. So if there is some constant, so that this log of lambda 1 divided lambda tilde is between these two numbers. Okay, so length of this omega c is so since g acts on omega, the any g will have some minimum infimum of the distance function it can move. Okay, so for every point there it moves certain distance. So you take the minimum of that distance moving. So of course it could be zero. Okay, right? But so then, so if this is satisfied, then you say it's satisfied the uniform middle eigenvalue condition with respect to this boundary hypersphere. Okay, so because this is one associated with the hyperspace space eigenvalue. So I mean the dually these hyperspace is eigen vector, or it's just eigen covector in this case. So that has some norm, and so we can, of course, we can do the G inverse, and then so this gives you equivalent condition under this same thing. Okay, so it gives you a condition on the top and the bottom eigenvalues. Okay, of this matrix, for all of this matrix. And of course, this means that this is larger than one and this less than one. And so this is a notation that if you have a f to an, then there's a path map sending taking the linear path, this homomorphism. So we'll use that notation here. And gamma b, so for this lemma, then so if you have some uniform middle eigenvalue condition with respect to BDA, then the linear path has some non-zero expanding subspace and some contracting subspace in Rn, because this is associated with lambda 1 and lambda n, right? So that's because this is really just uh, uh, right, right. I mean, I guess I should just consider this as a upper left corner of H, and then this makes sense. Okay, so we need to prove this theorem. So the basic proof is that we work with some these unanswered flows. So omega has a Hilbert matrix. So let's take a unit tangent bundle of sigma omega. So this is just take the tangent bundle and then you remove the origin, I mean the zero section, image of the zero section. And then any two are equivalent if they're the same point and they're related by some positive scalar. And an is so in that case, so you can just define unit bundle, tangent bundle over like this, and even though you don't have a metric, and then we take so we take this UA times AN, and suppose this H is some representation. So maybe this H is not so good, but anyway, so let's look at this H, this notation. Then and then you act by GXU bar by this, okay, and which is just when the unit tangent bundle is just X normally, and then for a point in the affine space, you act by this affine transformation HG, and then you take the quotient. Okay, so you take the product, and then you take the quotient, and then this will fiber over this space. Okay, with the fiber is always some this AN isomorphic to AN. Okay, and then maybe I should say isomorphic because there's no canonical way to identify with AN. And then let's say Bn be a vector space associated with AN, then we can form this product. And then again, we take the quotient, but we just take the linear part with the quotient. Then you can define a flow in this space. So this is a unit tangent bundle. Then there's a geodesic flow always. Okay, so this means that we start at any point and use u omega and then u omega gamma gamma. So this is really the unit tangent bundle of this quotient orbifold omega mat gamma. So you take the vector and then you flow along and then you come back to at t you go to some other unit tangent vector. Okay, so I mean by unit tangent vector the equivalence class here. Okay, that is, and so this will induce a geodesic flow. Okay, and then you can define this flow on A by just because you can on the A tilde, which is just the product. So you follow along the geodesic, and then in the second factor, you just do the trivial action. Okay, and then you take the quotient. Okay, so even in the product, A tilde is of course trivial, but in the quotient, it may not be, right. It's not really trivial. And then for B, you can do the same. B, you extend in the second factor, you act trivially, but in the quotient, we have some non-trivial flow. And also, you can define this fiber metric, which is just the fiber-wise inner product. So this means that you just take for each point, you just take some arbitrary fiber-wise inner product. But of course, the way to construct it is you cover by some compact sets, and then you choose some metric over here, maybe constant metric, and then you sum by partition of unity. Okay, that's and then so this will give you, and then we have this trivial flat affine connection here, and then this has a flat linear connection. Okay, so affine connection means that it's not just linear. You can translate these. I mean, these parallel translation could have translation vector. Linear means that the parallel translation is always linear. Okay. Okay. So we have some flat bundle and then flat affine bundle, and then here you have flat linear bundle, and then of course, right. So then we want to decompose into this vector bundle B into three parts. Um, so for each u in the u omega, you have some maximum oriented geodesic ending at the backward endpoint and then at the forward endpoint. Okay, and this so each of these endpoints are just one-dimensional vector spaces actually. Okay, and then this is bound. You call that this is C1 because it's strictly convex and C1, right? Which is proven by Benoit, right? We have a gamma is compact orbifold case. So then there's a supporting hyperplane space is H plus and H minus at each of these. And then you take the intersection. So these take place or in this boundary AN. So this SN minus one infinity. Maybe I missed infinity here. And so this corresponds to vector space of codimension 2 in the B tilde. Okay. So for each vector u, you define this 3D composition, and of course this map sending to the endpoint is C1, and then to hyperspace is also C1. Is continuous, so these are continuous bundle. So these are topological decomposition, okay, and then so over L, you have this decomposition, which is actually constant, right? So it doesn't, as you go along, you don't change these endpoints and also the hyperspaces and these things. So the flow we define is actually well defined, and so this is in the backward direction, this is the forward direction, and so on. Okay, and so if the G acts on this complete affine geodesic with unit vector in the direction of and correspond to the endpoints, and they have some eigenvalue corresponding to lambda one and the smallest eigenvalue of the linear part of LG. So then let's see that so let's look at the geodesic with that property. Let's say okay. Of course, I mean it doesn't have to happen that property, but let's look at that property. Right. In the word hyperbolic strictly convex case, that is always true, right? Okay. But in non-strictly hyper convex case may not be. But anyway, so here act by this expansion, and then here act by the contraction. Okay. And so this flow you can define here, and then you can also define the flow on this. A tilde. So we did define for B tilde, right? And then we define for A tilde by just again using the geodesic flow and then trivial factor on A in these other factors. And so we define this flow by unit tangent bundle. And so this linear part also will preserve this decomposition. And of course, the deck transformation group will also preserve the decomposition here. And so with respect to fiber, you can also show that actually this expanding in the B plus, and then it's actually contracting in the B minus as you flow in the positive direction. Of course, if you go in negative direction, it will be reversed. But for some constant here, so constant is not so clear what that is, but so I guess maybe I should say C is bigger than one, but okay, that's probably better. So we will prove that this property holds for C big enough, and then uh, so for some T1, and then if this is true for some T1, then you can choose different C, so bigger C to make it true for every T. Because this is just the property of the dynamical system. So there's some decomposition. So if something is contracting at some time t, then it will at every point, then on a compact set, then it's always you can show this property everywhere. Okay. Okay. So that's basically what we will prove in proposition 421 that there is some T1 where this is contracting and this is uh, so contracting for the B minus and then contracting for B plus for the negative T in this case. Okay. So that's so instead of proving expansion, we prove this property. So that's the equivalent. So the way to do it is to show that there's some there's some big enough T and then that are so the proof is by contradiction. So if there is no such thing, then the uh, these mm, right. So we will use this lemma 4.2.1 and 2.5. Okay, and okay. So here, but of course, so we just need to do it for B minus because it's a symmetric argument. So I just need to prove that this is contracting uniformly as t goes to infinity. Okay, so that's what I need to show. Okay, and here, so these are just some lemmas to prove before that, and so that's just that these lengths it goes to zero infinity as these um, right. So G is actually always some so if gamma x like this, then you can assume that this is so if you have some infinitely many elements sequence, then you can assume that these are by taking subsequence some positive biproximal elements because I mean the torsion elements will be always kind of uh, not go to infinity, right? Of course, uh, right. Anyway, so you can prove this theorem up to some finite index, so you can assume that these are all positive. Any sequence is all positive biproximal, and then they will also have attracting and repelling fixed points, which are unique. And the length will always go to infinity. Okay, so if you have infinitely many of these, okay. Okay, so right. Yeah, I mean, in the case when these fixed points are converging, right? So if it converges, then the length has to go to infinity because they are all distinct, right? Right. And then the lemma 2.5 is that you choose some positive is this AI and RI are convergent. Then for any compact set in if you remove some limit of this, so if AI and AI are like convergent, then for any k, this will always converge to that point uniformly. Okay. So this is a sort of a convergence theory thing. So you can always do that. Okay. So I think it is depending on fixed attracting points converge, and then these are distinct, and then these are different. Then you can always show this property. Right. So the key point is to prove this lemma, and then so thing is to show that if this is not the case, then we will obtain contradiction. So we take some fundamental domain here, and then so in the omega, so we choose any sort of sequence xi in F in the fundamental domain, uh, and then you choose unit vector in the for the unit vector here. Okay. So xi is a unit vector here. So you can always extend this to by geodesics, and then these are the beginning points. I mean the backward endpoints, and then the forward endpoint. These will be the backward endpoints, uh, and then we'll show that this it goes to zero here, and so. Uh, right. So for any sequence, okay, Ti. So if you can show for any sequence this happens, then this is actually uniform, and then these xi's choices are arbitrary, and then you show this kind of fact for any sequence and any Ti, then this is actually uniform convergence. Okay. Right, because if not, then the if it's not uniform, you can always contradict whatever I'm trying to prove. Okay, so. Right. So uniformness can be proven this way. So then you just look at yi, which is the flow of xi after some time ti, and then you look at the sequences, and then I put this gi back to the fundamental domain by some gi because the action is co-compact, and then we act by this linear part of the action, and then and then we can so for this argument you can choose these so that AR and RI convergent. You just take the subsequences, and then these so if these are the same, you can multiply by some element to make it different, and then this is true, okay, for any k, and then so GIRI will converge to so if this is different, then you can always show that this segment just converge to a star by this whatever I showed. So that's not true. So what happens is that this is only case. GR star is the y minus and y plus is this. So this case is also absurd. You can also show that. Uh, so then we can show that basically that these right. So these all converges, and Ti be the other endpoint, and then they also converge and lie in here, and so on. And then so Gi also has an invariant gray sphere containing the attracting fixed point AR, and then we can show that R is uniformly bounded distance here. And so the key point is that uh, right. So there's a lot of argument, but then the key point is that this is a bounded sequence, and right, right. So the key point is we decompose into the once pi minus into the path parallel to Ri, and then parallel to this ds. Okay, so this attracting fixed point, the sphere containing the attracting point fixed points. And the point is that along Ri is always contracting, so it's contracting, and and you can show that actually because this is converging to y minus, this part is also uniformly bounded along some Euclidean metric, and this ratio is always bounded because these yi converge to something outside this, and so on. So, but we know this is zero, because this linear part goes to zero because this is a repelling fixed point. Okay. And so because the ratio is bounded, so this part also goes to zero, so the whole thing goes to zero. So bi minus is the bi v minus bundle, so therefore this whole thing goes to zero. So that was what we were trying to prove. Okay. Okay. So we proved this convergence property, and then then I will talk about the neutralized section in the uh, after 5 minutes break. Okay.